Hi, my name is Daniel Gu, and I am a grade 12 student from Bill Carruthers Secondary School, here to teach you how to solve question number 2, section 4.1, mid-chapter review of advanced functions. So let's begin. So, Jude is diving from a cliff into the ocean. His height, in meters, above sea level is represented by the function h at t equals negative 5 bracket t minus 0.3 bracket squared plus 25, where t is measured in seconds. So, to begin, highlight some of the key information such like the function itself, the height and its unit in meters, and t, which its unit would be in seconds. Just to reiterate, Jude is diving from a cliff into the ocean. His height above sea level in meters is represented by the function h at t equals negative 5 bracket t minus 0.3 bracket squared plus 25, where t is measured in seconds. So the first question asks to expand the function. The function itself is in vertex form already, and to begin, we need to be able to expand the t minus 0.3 squared. So let's recall back to multiplying two binomials by each other. So you want let's for example take x plus 3 as the first binomial and x minus 2 as the second. To solve for this, you want to take the x in the first binomial and multiply by the x itself in the second binomial and the minus 2. And then do the same for the 3. So it'll look like this. I got here by doing x times x, then x times minus 2, 3 times x, and then 3 times minus 2. And then you'll get x squared plus 3x minus 2x minus 6. And you can further simplify this to x squared plus x minus 6. So now that we know how to multiply two binomials together, let's begin. So the function, which is in vertex form, h at t equals negative 5 bracket t minus 0.3 squared plus 25. You want to keep the minus 5 and first break the t minus 0.3 into 2 since there's a square right there. Now you can see the two binomials here, which is why I wanted to do this here. So we do the same thing we did right here in the recall and multiply everything in the first binomial by everything in the second binomial. So t squared minus 0.3t minus 0.3t again, and then you want to do equals positive 0.09. Don't forget the plus 25. Now, to further simplify, this would be negative 0.6t plus 0.09 bracket plus 25. From here, we need to expand further with the negative 5 going into each of the terms in this bracket right here. So minus 5 times t squared equals negative 5t squared. This equals plus plus 3t, 3t minus 0.45 plus 25. And then you can just simply collect like terms, so negative 5t squared plus 3t, and then positive 24.55. So there's your expanded function in standard form. Question B, how high is the cliff? So we know Jude is diving from a cliff into the ocean. And so the start of the function will be at the height of the cliff. And so time will equal to 0 at the height of the cliff. To understand this better, I'll draw you a little diagram. So there's a cliff. Let's call it cliff. And you have Jude standing right here. If this were to be a graph with the x-axis and the y-axis here, this would be 0. And let's just say this was any number. Basically what I'm trying to show is Jude begins at the top of the cliff and will end off somewhere below sea level. So to solve for this, we want to put t at 0 for the standard form formula. .55 when time is at 0. This value is basically the height of the cliff. So therefore, the cliff is 24.55 meters for the units high. This value of 24.55 is also called the y-intercept. Question C. When does Jude hit the water? So, using standard form, we could find the two x values when we could find two x values when y equals to 0, and what that basically means is finding the two x values when Jude will be in contact with the water at sea level, which is basically y equals 0. So if y equals 0 represents sea level, we can use the quadratic formula, which I will label as QF, which is minus b plus or minus square root b squared minus 4ac divided by 2a. And the values for a, b, and c are -5 for a, 3 for b, and 24.55 for c. Using these three values, we're just going to insert into the quadratic formula to find the two x values when y equals 0, which is sea level. Since there is a plus or minus, we want to do two things from here. You could take minus 3 minus square root 500. Oh, sorry, which we already did. Minus 22.3607 divided by minus 10, which will equal, keep the x values there, which will give us positive value of 2.54. And if you're to do -3 plus 22.3607 divided by minus 10, x would equal negative value of 1.94. Immediately deny the negative 1.94 since this would have to mean that Jude is jumping backwards instead of jumping off the cliff to the sea forwards. Now all we need is the positive value of 2.54. X is equivalent to t since in the function h at t, the t is just a substitution for x. This means that at 2.54 seconds, Jude will land and hit the water exactly. Therefore, Jude hits the water 2.54 seconds after jumping off the cliff. Part D, determine where the function is negative. So, I'm going to read out the answers first and then explain to you why this happens. So when t is greater than 2.5, the function is negative, meaning that Jude is in the water. When t is less than 2.5, the function is positive, meaning that Jude is still in the air. So what I mean by this is for x values in between 0 to 2.5, Jude is still in the air, making all y values positive. And when Jude from times 2.5 and on, all y values are negative, meaning he is in the water now. A real-life example that uses parabolas and the quadratic function is when a pitcher throws a baseball. It follows a parabolic path, providing a real-life example of the graph of a quadratic equation. The parabolic function predicts if the ball arrives in the batting range for the particular hitter and the time between it leaving the pitcher's hand and crossing the plate. There are many real-life examples of such shape ranging from video games to engineering. Another example would be for an engineer, someone who designed a bridge. The cables and arches that support bridges often allow the shape of a parabola. This allows the engineer to maximize the weight supported while minimizing the material the bridge requires for construction.